Welcome everybody. This presentation is entitled From If Then Else to Deep Learning. My name is Bart Baesens, and let me maybe start with a brief introduction about myself. So I'm a professor of Big Data and Analytics at the Catholic University of Leuven, where I also studied. I graduated my master's degree Business Engineer in Management Informatics in 1998, and then I continued with a PhD. The topic of my PhD was developing intelligent systems for credit scoring using machine learning techniques. So it was essentially about using neural networks, but then shallow neural networks instead of deep learning neural networks, as we will discuss later, for credit scoring. You can find my PhD at my website, www.dataminingapps.com. On that website, you will also find our different research tracks. So I have a team of about 8 PhD students, all co-supervised with some of my colleagues, and we work on a variety of different topics. We work on marketing analytics, fraud analytics, credit risk analytics, and HR analytics. And we study those different application fields both from a technical perspective as well as an application-oriented perspective. More specifically, we study the development of new algorithms, new techniques, new ways of analyzing data. I will report on this later on through the presentation. Next to the development of new techniques, new algorithms, we also study how those new algorithms can be successfully used in those particular business settings. So that means that we're going to focus on business-specific criteria, such as profit, such as interpretability, such as regulatory compliance, and so on. If you'd be interested, you're going to find lots of free stuff on my website, including presentations, including e-lectures, etc. We also feature a 2-weekly newsletter, which we send out for free. So in case you'd be interested, you can register on that on dataminingapps.com. I'll also put this presentation on there for download. Here you can see some of my example publications. I've written a couple of books on big data and analytics. You can see them listed here. You can see the first one, upper left corner, is probably my most successful book. Analytics in a Big Data World has been translated into Chinese, as you can see right next to it, and will also be translated in Korean. Some other books on fraud analytics, credit risk analytics. Our most recent one is Profit-Driven Business Analytics, which should be available on Amazon from the beginning of October onwards, so in a few weeks from now. And the one that we're working on right now is in the lower right corner. It's Principles of Database Management. It's going to be a quite big book. It will have 20 chapters. And it covers the entire realm of database management, starting from legacy databases up to relational databases, up to NoSQL databases, and so on. And in the book, we discuss how to develop logical data models, internal data models, external data models, and how to work with them both in a small and big data setting. Anyway, let's start with if-then-else rules. Well, if-then-else rules will probably the first type of artificial intelligence systems that were used by companies already a few decades ago. And the first type of rules were expert-based. That means that they were not based upon data. They were not rules that were learned from data, but learned from the experts instead. So you can think of a domain expert. That could be a marketeer, that could be a credit analyst, that could be a fraud analyst. And many of these experts have gained experience, business knowledge, by having worked in a particular business setting. And all this business knowledge was then written down into expert-based rules. Expert-based rules are still being used in domains such as fraud detection. If you look at anti-money laundering applications, for example, many of these systems nowadays are still based upon expert-based rules because they perform very well. So expert-based rules are not to be frowned upon as inferior to data-driven rules, which I will discuss in a moment. Expert-based rules are very valuable also in an analytical setting to steer the analytical development process. Not only to steer it, but also to validate it afterwards. Think in a credit risk modeling setting, for example. You don't need an advanced deep learning neural network to tell you that the more debt a person has, the less his or her creditworthiness. Right? So if your data mining system tells you that the more debt a person has, the lower the creditworthiness, then that's a nice validation of your expert-based knowledge. Besides expert-based rules, you can also make use of data-based rules. And these are rules that have been learned from underlying data sources that have been gathered from a variety of different domains, right? Could be different data sources that you link together and from which you will learn data-based rules, right? And that you can do using any rule induction technique. Could be a decision tree technique or just an ordinary rule induction technique. There are plenty of those techniques on the market. The important thing to remember from this slide is that both expert and data-based rules complement each other, right? That's really very important. So I'm not implying with this slide that we should abandon expert-based rules and go to data-based rules. Another thing to remember is the fact that they are rules. The fact that they are rules makes them highly interpretable to be used in a business setting. Let's have a look at the analytics process model before we get into the more technical side of deep learning and relate it back to our if-then rules. So here you can see the analytics process model highlighted. So we typically start from a business problem. That could be assessing the creditworthiness of your mortgage customers. Or that could be seeing what customers or determining what customers are likely to respond to your marketing campaign. Or that could be label transactions as fraudulent, yes or no. Think about payment transactions, for example. So once you have identified your business problem, you need to identify all the data sources that could potentially be useful to solve that business problem in a data-driven way. Right? So you identify the data sources, then you select the relevant data and bring it together into a staging area. And that staging area could be any type of data source. Could just be a plain vanilla Excel file if you want, or even a plain vanilla CSV file, which is still commonly used nowadays as a staging area. Or it could also be something more sophisticated, like a NoSQL database. Then we're going to clean the data. And clean the data means that you're going to get rid of all the inconsistencies because your data is going to be contaminated with noise. Think about somebody's age being 200 years, or it's going to be contaminated with missing values. Think about somebody's income is missing. Then you will transform the data, and that's a really very important step because in this transformation step, you're going to learn features. What is a feature? Well, think of age, for example. No company stores the age of their customers because it changes on a yearly basis, hopefully. So that's why companies store date of birth, and they derive a feature from it, like age. Age is being derived by date of birth. That's a manually engineered feature. That's really very important because you have to write a very small routine that subtracts the date of birth from today's date to determine the age. This is a manually engineered feature. Basically, in this transform the data step, you're doing the feature engineering. You're deriving features, most often in a manual way. And you derive those features based upon your business insight, based upon your experience, etc. And once you have carefully engineered all these features, you can start analyzing the data. And you can build an analytical model which will differentiate or discriminate the churners from the non-churners, the responders from the non-responders, the fraudsters from the non-fraudsters. And once you have built that model, you can start interpreting it, seeing if there are some novel insights in there. Some of the insights may be confirming your prior business experience, which is nice, but some of the insights may also be entirely unknown. So that makes it also very interesting. And you're going to deploy the model. That means that you're going to represent the model in a user-friendly way such that your decision makers feel comfortable with it, trust it. Let's give you some examples of analytical application. Here you can see an example of churn. Churn means that you want to predict if customers are going to leave you, yes or no. Think about a telco setting. Many telco operators are being confronted with rather high churn rates, so they would like to know why customers leave them. And we can do that using all types of characteristics. You can look at the age of the customer. Age is a feature. I can look at the gender of the customer. I can look at the calling behavior of the customer, etc. 3 types of very interesting features that you often see popping up in a churn prediction exercise are the RFM features: recency, frequency, monetary. Recency means how long ago has a customer made a purchase or a transaction. Frequency is the number of transactions per unit of time. Think about, for example, the number of calls per day. Monetary is the average amount of the transaction. Could be average amount of the transaction, could also be maximum amount of the transaction, depending upon how you want to define it. These RFM features are examples of features that you engineer, that you manually engineer. Marketeers have given us the insight that the RFM features could be very relevant for predicting churn. Hence, we will use them in our analytical modeling exercise. Very important to remember from this slide is that those features are manually engineered. When I say manually engineered, I mean us experts or data scientists have to define them during the analytical modeling exercise. It's not the analytical technique that will define it for us, but we have to define it. We have to make sure that we include it in the data set. This precise set of same features can now also be used to predict CLV, customer lifetime value. Instead of churn, yes or no, which is a binary target, we now have a continuous target, which can range between 0 and whatever upper bound. And that same set of features can then also be used to predict your continuous target variable. Those RFM are just one set of features that have been commonly used in a wide variety of marketing analytics applications, ranging from churn prediction, which was on my previous slide, to CLV modeling, which is on this slide, to response modeling, to customer segmentation, and so on. They're very powerful variables, but they have one limitation in the sense that they were manually engineered. It would be really cool, it would be really nice if we start from a data set and then have it analyzed by an analytical technique, which is going to automatically learn those features. And I can already tell you that that will be the case with deep learning, as we will come back to in a moment. In terms of industry standards, analytical industry standards, well, linear and logistic regression are the most commonly used techniques for predictive analytics. Here you can see both illustrated. At the top, you can see my CLV example again, which is linearly related to recency, frequency, monetary. Below, you can see a logistic regression model, which will predict the probability of churn given recency, frequency, monetary, and so on. So if you carefully look at that logistic regression model, to the right, you see 1 divided by 1 plus e to the power minus the linear combination. Basically, this e-power transformation is being conducted to make sure that the output is always bounded between 0 and 1 and can thus be interpreted as a probability. Linear and logistic regression are commonly used in different industry applications, ranging from churn prediction to response modeling to credit scoring. It is especially useful in credit scoring. For example, if you have a credit card, you have a mortgage loan, you have a car loan, logistic regression will be used to predict your probability of default. And why are these techniques so useful? Why are these techniques so commonly used? Because of various reasons. First of all, because they usually perform well, as we illustrated in various benchmarking studies in our own research. And secondly, because they are easy to interpret. So it's not only about model performance, but it's also about the interpretability. Because at the end of the day, for an analytical model to be used, the business user should feel comfortable with it. He or she should have trust in it, which is really very important. And this is exactly where these models excel at. They give good performance, and they are interpretable, easy to understand models that can generate trust in their usage. Another type of model that has been very popular in the industry are decision trees. Here you can see an example of a decision tree. It's a top-down structure, which you evaluate so top-down way. So you look at whether frequency is bigger than 5, yes or no. If yes, you look at whether recency is less than 2, yes or no. If no, you decide churn. If yes, you decide no churn. Very important to note here is that this is a statistical/analytical model. That means if frequency is bigger than 5, yes, and recency is less than 2, no, it does not imply that all of these customers will churn. That's not true. It basically implies that a majority of these customers will churn, right? So these are statistical rules. Decision trees have also been commonly used in analytical applications. Why? Well, pretty much because of the same reasons for linear and logistic regression. Because they yield very accurate solutions, 1, and 2, because they're highly interpretable. That's why we also see them being used in credit scoring, especially during the pre-processing step of credit scoring, to understand some initial patterns in your behavior, in your data. But they've also been used in churn prediction or other settings where interpretability plays a key role, such as medical diagnosis, screening patients and deciding upon patient follow-up, for example. That brings us to somewhat more advanced analytical models, which are neural networks. Neural networks are often referred to as mathematical representations inspired by the functioning of the human brain. It sounds very attractive at first sight, but basically neural networks can pretty much be related or to statistical origins. They basically originated starting from a logistic regression model. Here you can see a logistic regression model visualized as a neural network. So you can see you have one neuron, which is in the middle, and that one neuron has various inputs. So it has a recency, frequency, and monetary feature that serve as input. That one neuron will then perform certain types of internal processing and generate an output. Right? This is a one neuron neural network. It's the most simple type of neural network, and you can very easily relate that to both logistic regression and linear regression without having to resort to biological theory of how your brain works. Here you can get a little bit more insight into the internal functioning of that one neuron. The one neuron takes recency, frequency, monetary, and every neuron always takes a fixed input, an input that is always fixed to the value of 1. You can think of that as a term which is very similar to an intercept term in a linear or logistic regression, right? An intercept term, beta 0, for example. Each of these 3 features and that intercept term has corresponding weights, W1, W2, W3, W4. Those are the weights that you will have to estimate during a learning process. In other words, those are the weights that you will have to learn from data using a certain type of optimization criterion. The neuron performs 2 types of activities. Every neuron performs 2 types of activities. It computes the sum of its weighted inputs. So it's going to do recency times W1 plus frequency times W2 plus monetary times W3 plus 1 times W4. That's the sum of its weighted inputs, and it will then transform that using a transformation function and yield the output. Various types of transformation functions can be thought of like exponential, linear, hyperbolic, tangent, and usually this is something that as a data scientist you don't have to choose yourself. Usually your software will have very good default settings for that. The idea is now not to use one neuron, but to use different types or several neurons and arrange them into layers. And here you can see a first type of neural network. A first type of neural network whereby we have our input layer, right, which has recency, frequency, and monetary. And now we arranged 3 hidden neurons in a hidden layer, which each give one particular type of output, which is then fed into the output layer in the output neuron, which then gives me my final output. So you can see this is a pretty complex structure where information is being processed from left to right. So you get recency feature, frequency feature, monetary feature, feeds in the neural network, and out comes an estimate for the CLV, right? And each of these neurons performs their own specific processing. Each of these connections has weights associated with them. Remember, these weights need to be estimated during a learning process. So you can see this is a neural network, and this is what we would often refer to as a shallow neural network. That means a non-deep neural network. Why? Because it only has one hidden layer. You can think of neural networks that have more hidden layers, and these are what we would call deep learning neural networks. Why is the difference important between shallow and deep learning neural networks? Well, essentially what this hidden layer does, it's a feature extractor. It learns the features from the data. So one hidden neuron in your hidden layer can focus on a particular combination of recency and frequency. Another hidden neuron can focus on a particular combination of frequency and monetary. And another hidden neuron can kind of transform the frequency feature in a particular way. So this hidden layer essentially detects or learns features. So that means that with neural networks, we no longer have to manually engineer the features, but the features are being automatically learned by the network itself. So the network can learn very complex features, and as such, optimize your analytical model. That gives it a very strong competitive edge when you compare that to linear, logistic regression, or decision trees. But we always have the no free lunch theorem, which means we have to pay a price for that. The price for that is that, first of all, this is more computationally intensive. And secondly, the model that we essentially obtain is a black box model. It's a very complex model which will be hard to explain to a business user. Right? We'll come back to that in a moment. These shallow neural networks with one hidden layer have often been used in applications such as fraud detection, when you're especially interested to detect fraud, but not that much in fraud prevention. Why? Because in fraud prevention, understanding is very important. If you want to prevent fraud, you have to know how the fraud occurs such that you can implement certain types of checks that will prevent fraud. These shallow neural networks have also been used in response modeling to see whether somebody is likely to respond to a marketing campaign, yes or no, or in forecasting. Let's now continue and look at analytical evaluation criteria. Because if we put an analytical model into production, what are the criteria that it should satisfy? Well, those analytical models should be accurate in a statistical sense. If you build an analytical model for fraud detection, your model should discriminate the fraudsters from the non-fraudsters, right? According to specific statistical performance criteria. In certain settings, not in all, you also want interpretability. In credit scoring, your model should be interpretable. Right? We cannot just use very complex neural networks and use that as our primary credit scoring tool. Because if I would be rejected by a very complex neural network for a mortgage, then I would like to know why am I rejected, right? So I need interpretability. Operational efficiency means the time required to build the model, run the model, and then afterwards also post-process it. And finally, an aspect which is often forgotten in analytics is the economical cost. How much, or profit in other words, how much profit is the model going to give us? In one of our most recent research tracks, we work on profit-driven analytics. And we directly embed profit in the analytical technique. We have developed prof-logit models, which are logistic regression, but with profit embedded as its optimization criterion. Profit as opposed to the traditional maximum likelihood optimization. We're currently working on prof-tree, which are profit-driven decision trees, which directly optimize profit instead of reducing impurity using entropy, Gini, and the like. And we also wrote a paper on prof-ARIMA, whereby we're going to evaluate ARIMA forecasting models using a profit measure. When I look at deep learning is going to focus on one of those 4 evaluation criteria, and it will focus on accuracy, right? It will focus on developing highly accurate analytical models, and to do so, it will sacrifice some interpretability, some operational efficiency, and potentially also some economical cost. And here you can see all the models that we have discussed, all the techniques that we have discussed before, but now contrasted in terms of their performance, interpretability, operational efficiency, and economical cost. So you can see that linear and logistic regression are good in terms of performance, interpretability, operational efficiency, and cost. Decision trees are a bit better in terms of performance and in terms of interpretability. They do have some advantages with respect to linear and logistic regression that I cannot comment on right now, but if you'd be interested, you can have a look at one of my books in which we discussed decision trees. Neural networks, which you can at the moment kind of consider the same as deep learning. Later on, we're going to come back to the relationship into more detail. Neural networks are going to predominantly focus on performance, on statistical evaluation criteria, and they're going to sacrifice some interpretability, some operational efficiency, and some economical cost. This is basically based on a whole range of benchmarking studies which I conducted with some of my colleague investigators. Now, let's come back to that interpretability issue. In certain settings, white box applications are highly needed. Think about credit scoring, for example. There we have Basel and the recently suggested IFRS 9 guideline, which basically enforces the use of white box applications. And white box is a very subjective term. It refers to the interpretability. The analytical models should be interpretable to the decision maker. We also need it in medical diagnosis to understand why certain medicines works or certain drugs do not work. We also need it in fraud detection, especially if we're aiming for prevention, because it's not only detecting transactions as fraudulent, yes or no, but it's also about understanding why certain transactions are fraudulent such that we can prevent them later on from becoming fraudulent. In certain other settings, black box applications are fine, right? Black box applications could be fine in settings where you don't care about interpretability. And there exist settings like that, like response modeling, image analytics, text analytics, etc. And that's where deep learning will play an essential role. And there are various triggers that actually contributed to the emergence of deep learning. First of all, when we do deep learning, we need very powerful computing facilities, and the emergence of graphical processing units and even tensor processing units by Google, for example, has contributed to the interest in deep learning. Parallel computing platforms, cloud computing, NoSQL databases. As we will see later on, deep learning is especially well suited to tackle unstructured data. NoSQL databases, think about MongoDB, etc. They're very good at storing unstructured data. And then right now we also have all kinds of software platforms that facilitate the development of deep learning applications like TensorFlow from Google, Keras, Theano, Caffe, Torch, and Lasagna. Now, what is deep learning? In a nutshell, and put very simply, well, we don't have time to get into all the different types of architectures, but a deep learning is essentially a multi-layer neural network. So instead of having only one hidden layer and having a shallow neural network, we're going to work with a deep learning neural network which has different hidden layers. And every hidden layer is a kind of feature detector. It detects features automatically from the data. And that gives you a very important benefit because now we can detect more complex features. And that's where deep learning is good at. It can really detect very complex features from the data. So every of those hidden layers, every of those hidden neurons in each of those respective hidden layers essentially is a feature detector, but now a complex feature detector, right? And those deep learning neural networks have been proven to be very successful across a variety of applications. Most of these involve unstructured data. That's very important. Unstructured data like images, like audio and video, unstructured text data, sometimes also recommender systems, sometimes also music applications and gaming, for example, right? Think about Google's AlphaGo game that was also tackled using deep learning. Let's give you some examples. To the upper left corner of my slide, you can see an application of image coding. So you can use image coloring, You can use a deep learning neural network that learns how to color black and white images. So you give it a training set of images of which you, for example, manually colored or using a set of expert rules. And once you've given it a training set, it will learn to automatically color images. And it will learn to basically color any type of image. Deep learning can also be used for image captioning. So you can see to the right, you can see a dog jumping over a bar. Well, deep learning neural networks can be used to learn a description or a caption of that image, like it's a black and white dog jumping over a bar. It can also be used to detect objects. Lower left corner. You can use a deep learning algorithm or a deep learning neural network to detect all the objects in the picture, like an elephant, and you can also detect that the elephant is brown, that the elephant is standing. You can detect the green trees in the background, a ball which is white, etc. It can also be used to translate text from an image. So in the lower right corner, you can see an image, and there's some text on there, and I don't know what language that is, but it looks pretty complicated. And a deep learning neural network is going to extract the text from there, much like OCR would do, and then translate it to the language you want. Obviously, what's really very important is that all these deep learning algorithms require training sets of data such that they can estimate their parameters, their weights. Here you can see some examples of deep learning into a little bit more architectural detail. A commonly used type of deep learning neural network is a convolutional neural network, which you can think of a multi-layer neural network, as I said before, whereby every layer detects certain features of your input elements. In this particular case, the input element is an image. So to the left, for example, at the bottom of my slide, you can see an image of two boats, and the neural network is going to process that image. It's going to learn all the complex features from it. And to the right, you can see that the neural network has 4 types of outputs it can predict. It can predict whether the image contains a dog, whether it contains a cat, a boat, or a bird. And you can see that the probability that it contains a boat is about 0.94, is the highest probability. So in this particular case, that deep learning convolutional neural network will decide that this picture contains a boat. To the bottom, you can see basically the same application, but with a flower instead. Now, those deep learning neural networks have also been used. Here you can see another example. This is from a Belgian firm. You can find the reference at the bottom, to start from a job description and to learn corresponding job titles, right? So again, starting from a training data set. Oftentimes, you can successfully build a neural network or a deep learning neural network, but not always. Here you can see an example of what we could refer to as a deep learning blooper, whereby the US Army wanted to use neural networks to automatically detect camouflaged enemy tanks. As already said, you need a learning data set. So a learning data set was provided of 50 photos of camouflaged tanks in trees and 50 photos of trees without tanks. If you ask me, first of all, I would consider this to be a very small learning set. I would not trust the results very well with this size of data set. And they built a neural network and then used an out of sample test set. That means a test set that that was not used during model development. And it turned out that the neural network perfectly classified that test set. So they gave that model to the American military, who started using this in some of their trials. And they found it to be not performing better than any random classification. Upon closer inspection, it turned out that most of the pictures that contained camouflage tanks were taken in cloudy weather, whereas most of the pictures with non-camouflaged tanks were taken during sunny weather. So basically, what the neural network learned was to discriminate cloudy from sunny weather instead of discriminating camouflage from non-camouflage tanks. So that's why it's really very important to make sure that you provide an unbiased data set to your neural network, and that you also understand up to a certain level what the neural network has learned. Deep learning has been received well in certain communities, but there has also been some criticism. And I refer to you to a Katie Nugget's contribution here at the top of my slides, which I can definitely recommend you to have a look at. And I copied some quotes from there. Too many startups and products are named deep something just as a buzzword. Very few are using deep learning actually. And I can agree with that because we've collaborated and sometimes we're being asked by startups to set up joint collaborations, and many of them try to use the word deep or deep learning more as a marketing term. Decision trees are not making headlines but silently beat deep learning in many Kaggle tabular data competitions. Very important remark. Another very important criticism is the legal nightmare of deep learning decisions that, even if correct, can't be explained. That's very important, right? And also, especially with GDPR coming up. GDPR, which means that we should carefully know how data is processed, what data is processed, but how it is processed. And that's really very important because deep learning focuses predominantly on the accuracy aspect. By sacrificing interpretability, this clearly poses a danger in settings where interpretability is very important. Think about if you would go to a bank and you don't get credit because there's some deep learning convolutional neural network trained using Bayesian methods telling you that you're not credit worthy. You're not going to buy that. You're not going to accept that. You're entitled to a little bit more explanation. Hence the importance of interpretability. One of the key questions is, how can we make deep learning neural networks interpretable? Well, remember, when we started this presentation, we started with if-then rules. If-then rules that you either got from a business expert or from your data. In my PhD, which I finished already in 2003, we studied how we can extract if-then rules from neural networks. That would be really cool, because then we have the best of both worlds approach. We have the accuracy from the neural networks and the interpretability from the if-then rules. Here you can see an example of a very simple neural network. It's a shallow neural network. Why? It's a shallow neural network since it only has one hidden layer. It has one hidden layer with two hidden neurons. Remember, those hidden neurons are the automatic feature detectors. In this example, the neural network is used to do credit scoring, to decide whether an applicant is good or an applicant is bad. Because of the Basel and IFRS regulations, black box models such as shallow neural networks and obviously also deep learning neural networks cannot be used as such for credit decision making. That's why it would be nice if we can extract if-then rules from it. In my PhD, I studied various approaches for extracting if-then rules from a neural network. We don't have time to zoom into each of these approaches, but I can give you the idea. The idea is to use the neural network and extract rules like you see right here. Here you can see a rule set which perfectly mimics the behavior of the neural network. So it tells us how the neural network thinks. This is very nice because now we have a rule set which is both powerful and a rule set which is white box, which is explanatory. That means if a certain applicant is rejected, we can give a clear explanation why the applicant is rejected by just detecting what rule has fired for this particular applicant. This rule set is interpretable, but we can even take it one step further and transform it into a decision table. Decision tables are a topic that have been intensively studied in a research group for already quite some decades right now. So here you can see a decision table, and it has 4 parts. Upper left part, you can see the decision criteria, right? Upper right part, you can see the cutoffs which are used to make certain classifications. So you can see like savings account, less than or equal to 12.40, bigger than 12.40, etc. The bottom part has the classifications. So here we're going to classify whether an applicant is good or bad. The decision table gives me a perfect alternative representation of my rule set. So you can see, according to the decision table, if savings account is bigger than 12.40, the applicant will be good. This is a key insight which was not clear from our rule set we showed earlier on. So decision tables can even give you that extra insight on top of the rule set, which allows you to further understand the patterns that reside in your data. That brings us to the conclusions. Deep learning, if you ask me, is a bit of a buzzword. Why? Because the techniques that underlie it, like multi-layered neural networks, have already been developed a few decades ago. Deep learning is now very popular because various hardware and software evolutions facilitated the learning of deep learning neural networks. However, we still observe a wide gap between academic research and business relevance. Far too often, academic research focuses on developing very complex techniques or fine-tuning very complex techniques without clear advantage to the business. So it's really important to bridge that gap, taking into account business relevant criteria. Business relevant criteria such as not only accuracy, but also interpretability, regulatory compliance, operational efficiency, and added value. If you ask me the impact of deep learning on structured data, I would say no. So if we look at relational data and if we look at classic analytical applications like credit scoring, churn prediction, I don't anticipate that deep learning will contribute a lot in those traditional applications using structured data. I do think deep learning has potential to work on unstructured data, such as image, video, audio, etc. Through the presentation, we also highlighted the role and impact of interpretability. In certain applications, like in medical diagnosis or in credit decision making, we do need interpretable systems because of regulatory compliance guidelines such as Basel, solvency, sometimes antitrust laws, etc. And that's why we also highlighted rule extraction methods in this presentation. Another type of models which I do strongly believe in and which I think has a lot of added value for business is graphical models like Bayesian networks. Bayesian networks are also commonly referred to as probabilistic white box models because they clearly show you how variables or sometimes even features mutually influence one another. And they also allow for a very quick and easy embedding of expert knowledge. To conclude, I would like to do a very small commercial for our book once more. So here you can see our book. We are currently wrapping it up, so we hope to submit the final manuscript in the next 2 weeks to our publisher, Cambridge University Press. In case you would like to stay updated, you can sign up on our website, pdmbook.com. We will put lots of free material on there. Obviously, we cannot put the PDF of the book on there, but we can put free slide decks available. So keep an eye on that website. In the next 2 weeks or so, we're going to put some free slides available on there. Thank you.